Hello everyone, this is your G. Today we will talk on a topic on hydrocarbons and that is reactions on alkene. This is the outline of today's lecture where we will discuss the various types of reactions on alkene. In introductions we will discuss what is alkenes and its behavior, and then we will classify the different types of reactions on alkene, and then is reaction discovery, their mechanism, why do we study it, we also discuss, and further we will discuss some MCQ on this topic. Now, what is alkene? A compound, chemical compound having double bond called alkene, and alkene reactions we mean that conversion of this double bond to other functionalities. Now, we can correlate the alkene different alkene reactions in the environment or to our surroundings, that we use the polythene bag that is from polymerizations of alkene. And again, when in the field there or ground there cutting a grass, and then we can smell a distinct smell that is of this volatile aldehyde, which is from the fatty acid present in the grass. Again, there is a when we keep the oil longer time, there is we can see some rancid in the oil. This is the unsaturation over the time gets saturated. And most interestingly, when we see that is the chemistry of alkene isomerization, that 11 cis retinal convert to all trans retinal. So how interesting, isn't it? Now we will discuss the classifications of reactions on alkenes. As alkene having the pi electron which is comparatively labile, so it is nucleophilic nature, and we can categorize these alkene reactions are here three categories. One is addition, another oxidation, and other few specific reactions. So we will discuss in the next few slides this addition and oxidation reactions. Now we will focus on addition reactions. Now we will discuss halogenation reactions. In 18th century, Joseph Priestley, Humphrey Davy and Michael Faraday, they are working on unsaturated hydrocarbons, and when they mix these hydrocarbons with different reagents, they could find that new interesting product is formed, and these hydrocarbons get converted to the other product. And here is the mechanism of these reactions. Initially they did not know how these reactions happen. Later this mechanism discovered. This is the way this halogen reacts with the alkene. This nucleophilic attack of this double bond to the halide and gives the cyclic halonium ion. Further, the another this halide ion attack from the back side of this halonium ion, and dihalide product is formed, which is the anti-stereochemistry. Now, limitation of this halogenation reactions is that when this halogen is chlorine or bromine, that cases this reaction happen efficiently, whereas in case of chlorine and iodine, the for iodine reaction is slow, and for chlorine it reacts violently, so difficult to control the reactions. And even if alkenes is larger in size, means more the bulky substitution is there, that cases the attack or halonium ion formation is very slow, and also this gives only anti-addition product. So these are the small limitation of these reactions. Now we will discuss halohydrin formation. In 19th century, when scientists are working on these reactions on alkene, and they could find that when they add the halogen in presence of water, then water as a solvent, then they could find the different product is formed, that is called halohydrin. This is the mechanism of formation of initially the cyclic halonium ion formed. Further, as in the reaction medium concentration of water is high compared to this halide, so water acts as a nucleophile and attacks from the similar the backsides of the halonium ion and gives the anti-halohydrin product. Now, this halohydrin formations also happen when they used that directly halohydrin means hypohalous acid like HOX. X means ClBr. Then halohydrin formation happened. And interestingly, we could note that this cyclic halonium ion also are like that. So nucleophile means solvent. Here water can add any of the side, but that side the nucleophile undergo attack where it generally formation of the stable carbocation possibility. So that side only nucleophile undergo addition. Limitation of these reactions are we could find that only anti-addition product possible and competitive side product as halide also present. So this dihalide product also are formed as a minor product, and also these reactions efficiently happen with chloro and bromo, but chlorine iodine also not reacts the same way, means it is slow and it reacts violently, so difficult to control. In these reactions, as water is a solvent, so but solubility is little issue, need to add co-solvent. Now we will discuss hydrohalogenation reactions. During 19th century, scientists when they are working on alkenes with treatment with different types of reagent, and they use the hydrohalous acid and they could find a new product. So this is the mechanism of reactions where this olefinic double bond undergo attack to the HX, and initial step protonation happen here. So protonation, after protonation this carbocation form and that halide react very fast to this carbocation gives this halohydrogenated product, and this is racemic product because the as carbocation generated, so halide can enter from any of the side. Now this type of reactions are happen, and scientist Vladimir Markovnikov studied the existing reactions, means there are many reactions in the research, in the literature. He observed every reactions and find that this when scientists use the symmetrical alkene in their reactions, then this halide addition any side of this double bond happen gives the same product. But if this unsymmetrical alkene is used for hydrohalogenation reactions, in that cases each every cases he found that halide attached to a particular side of double bond, and that means in this double bond this side or this side can halide attack possibility is there, but he found that he observed that only one side halide get attached, and there he given that one rule that means hydrohalogen addition to unsymmetrical alkene. What he given that rule by only looking on those product from that hydrogen, that is the positive end of the hydrohalous acid adds to the least substituted carbon, and the halogen the negative part add to the most substituted carbon because it form the most stable carbon. So this is called the Markov-Nikov rule, that most stable carbocation is generated. So that's why the hydrogen attached to the least side and halogen attached to the more substituted side. So we could see here one example, propane adds to the hydrobromic acid, that hydrogen adds to the least substituted position and bromine adds to the more substituted position. So this is because of the most stable carbocation formation. Limitation of this hydrohalogenation reactions is the rearrangement issue, gives sometimes unwanted product because of rearrangement, lack of stereospecificity of these reactions because of carbocation formation, no syn or anti-product. Earlier we have seen, but these cases, so stereospecificity is not happen because of carbocation formation. Poor reactivity with simple alkene. When alkene is very simple, then that cases that reactivity is slow, reactivity is very slow or even very poor, and the limitation here, no anti-Markovnikov product, only the Markovnikov rule follow, means most stable carbocation formation or most substituted the olefin carbon, most substituted center only attached with the halogen. In 1910, Johannes Thiele find the anti-Markovnikov addition product. When they worked with the conjugated diene with hydrobromic acid, he could find at high temperature 1,4 addition product form, where that bromine, the electronegative part, attached with the least substituted carbon, and that's why it is anti-Markovnikov product, because according to Markovnikov it should attach with the more substituted carbon. This is called, yet this is formed at very low temperature, that's why it is called kinetically controlled product, and at this product is formed at high temperature, this is thermodynamic control. In case of kinetically controlled product, this secondary carbocation formed at low temperature, and at the same time the bromine attack here gives this product. Another anti-Markovnikov addition product find Moireu et al. In 1928, when he used the conjugated alkene with hydrochloric acid, he find that instead of Markovnikov product, where the more substituted carbon attached with the electronegative part chlorine, the less substituted carbon is get addition with the chlorine, because we could find the intermediate carbocation here. If secondary carbocation form, that due to the electro withdrawing carbon is less stabilized, whereas the primary one in this case is stabilized. So anti-Markovnikov product form because of the substrate only. Another most popular anti-Markovnikov addition are discovered by Maurice S. Kharas. In 1933, he found when alkene reacts with hydrobromic acid in presence of peroxide, then instead of Markovnikov product, where bromine attached with the more substituted part, bromine attached here in the less substituted carbon. So this is the anti-Markovnikov product. As this happen in presence of peroxide, that's why this is called the peroxide effect. And how these reactions happen, we could find the mechanism. Here, if you use the peroxide, then peroxide decompose give the alkoxide radical, and that radical abstract the proton from hydrobromic acid, gives the bromide radical. Now this bromide radical initially adds to the alkene, so alkene gets homolytic cleavage, gives two radical, and now bromine can attack any one of this end. So if bromine attach this side, less substituted side, in its first, then it generates the radical which is more substituted radical, so more stable. Then it takes the proton again and generated bromine radical for further reaction. So the first step here is little different. For Markovnikov's case, first hydration, first protonation happen, gives the stable carbocation, whereas in case of peroxide, first bromination happen, gives the more stable radical, and then finally the hydrate radical adds, gives the less substituted, means the bromine attached to the less substituted carbon. Now we will discuss the hydration reactions. When water is added to the alkene gives the alcohol, then this is called the hydration reactions. Now, how this reaction discovered initially, the scientists tried to discover in 19th century the different reactivity of alkenes. They use the sulfuric acid and they find that this sulfate form, and then this water treatment gives this alcohol. And recently or nowadays in industry, alkene treated with hot water means that steam of water in presence of acid catalyst produce this alcohol. How this mechanism happen? Initially this mechanism could not understand, later mechanism of this reaction understand the same way. According to the Markovnikov explained that the first step is slow in presence of catalyst, that protonation happen gives the most stable carbocation, and further water adds this N to the carbocation. This reaction is fast, gives this product, and further this deprotonation gives this alcohol. Racemic alcohol is formed because this happens through carbocation intermediate, and limitation of this hydration reactions is that as this carbocation form, the rearrangement can happen. This group may shift sometimes, and also elimination is the one side reactions. Functional group tolerance at this happen if any functional group attached with the olefin, then there is also issue because of which is sensitive to this acid catalyst. Now we'll discuss hydrogenation reactions. In late 90s, the scientists Sabatier and Baptiste, they hypothetically thought that if they could mix hydrogen with alkene in presence of metal catalyst, then this can happen. And surprisingly, their hypothesis works, and the mechanism of work, these reactions happen in a concerted pathway. Hydrogen gas initially bind with the metal surface. Metals are palladium, platinum, nickel, rhodium kind of metal, and then after absorption, this metal hydride bond is formed, and alkene comes to the hydride side, and then in a concerted pathway this hydride transfer happen, and it happen the scene addition happen. So hydrogenations in the metal surface are seen in nature, so alkene generates the alkane. Now limitation of these reactions are these metals are very expensive, and also sometimes if this catalyst gets poisoning, then yield of the reaction gets less, and functional group tolerance are also issue because sometimes this hydride the affect the functional group attached with the alkene, and also sometimes this hydrogenation reaction requires this some pressure of hydrogen pressure needed. These are the limitation. Now we'll discuss hydroboration-oxidation reactions. In 1950s, Howard C. Brown planned an experiment when he was working with alkenes. He chose another reagent, diborane, and he planned reactions. He find that these hydroborations happen, gives this alkyl product, and syn addition happen. And further oxidations with hydrogen peroxide in presence of aqueous sodium hydroxide, he found that alcohol is the final product. And we could find that here finally the hydration product is produced. So this is the hydroboration oxidation reaction is the alternative hydration reactions. And most interestingly, we could find normal hydration gives here the hydroxyl group, means Markovnikov product is the more substituted alcohol form, that cases is the major product and main product, but this cases the less substituted alcohol is formed, the anti-Markovnikov product is the main product. So How these reactions happen? Here, this is the mechanism. This boron undergo addition to the alkenes in a concerted pathway. So this delta negative part attached to the more saturated double bond, and then this boron adduct form, and further this boron adduct, again this is hydrogen get a boron undergo reactions with the alkene. This trialkyl boron form finally, and this trialkyl boron again undergo oxidations with the hydrogen peroxide anion, and further we could see that the oxygen attacked here and gives this boron minus, and then as boron is negative, so alkyl groups shift to the oxygen happen and hydroxide leaves. So this way the three alkyl group again rearrangement to the oxygen happen when three times this hydroperoxide anion undergo reactions gives the alkoxide borate, and further this hydroxide minus ion undergo addition to this boron and generates this 3 moles of alcohol, the terminal alcohol, and this boric acid. So in 1970s, for extensive work on boron, and interestingly he solved that how to make this terminal alcohol synthesized. So he get the Nobel Prize in 1979. Now this reactions also some small limitation, like that it can't generate the Markovnikov alcohol, because we need the anti-Markovnikov alcohol, because earlier hydration addition gives the Markovnikov alcohol. This is regioselective in nature, so particularly less substituted side of carbon of alkene, the boron addition happen. This is regioselective in nature. Also, as boron is pyrophoric nature, so it's need to be proper reaction setting. Now we'll discuss the Oxymercuration-Demercuration reactions. In 1960s, Harvard Brown and his co-workers also planned another experiment. They used another types of reagent, mercuric acetate with alkenes in water solvent, and they found the anti-addition product is formed, and further they used the reducing agent sodium borohydride, and also he found that this hydration product. So this is also another alternative of hydration. This is the similar hydration product, Markovnikov product here formed. Now this is the mechanism we can see, oxymercuration mechanism. Here alkenes undergo the double bond undergo addition to this mercuric acetate in a concerted way and gives this cyclic mercurium intermediate, and further this, as water as a solvent is more amount, so as a nucleophile in undergo addition, backside attack happen. Also this attack on that side where generally generation of carbocation gives more stable, so that side the water addition happen and gives this intermediate again, and further this deprotonation gives this intermediate. This is the oxymercuration product. One side is the mercury, another side is the hydroxy group, and then the demercuration happen by using another reagent, sodium borohydride. So hydride undergo addition this mercury carbon bond via radical pathway and gives this product. So this is also demercuration product, and this is the hydration product. Now limitation of this reactions is the it can't generate anti-Markovnikov alcohol. Again this oxymercuration-demercuration gives the Markovnikov hydration product, Markovnikov type, and demercuration is non-stereospecific because it happens to the radical pathway. So this stereocenter are not retained during reaction. Also in these cases the mercuric acetate used where mercury is the toxic in nature, so this is the limitation of these reactions. Now we will move to oxidation reactions. We will discuss the permanganate oxidative cleavage reactions. In the mid-80s, scientists they planned and observed that when alkenes treated with potassium permanganate in basic condition and also hot condition, they could find that double bond get cleavage and gives this product. When this is all are substituted, that case ketone only the product. If there is hydrogen present in this side, then acid is the another product. Here the mechanism of the reactions, this alkenes undergo addition to the permanganate, the double bond undergo addition to this oxygen and gives this cyclic manganate ester, and further this rearrangement gives this ketone under heating condition, gives this ketone and aldehyde, and again this aldehyde in place of basic condition it undergo addition and this oxygen to another permanganate gives this intermediate, and further this rearrangement gives the acid. So the limitation of this reaction is that potassium permanganate is a strong oxidant, so sometimes over oxidation also happen if there is any other functionality attached with the alkene that sometimes get oxidized, and these reactions also harsh reaction conditions, so basic conditions even the strong basic solution used or even the heating condition required, so that's why it is a harsh reaction condition. Also low functional group tolerance if any functional group attached with this alkene, so that cases that functional group can get damaged, and this MnO2 the side product is formed in this initial oxidation state. This is thick in nature, so during your workup of reaction that could hamper your product yield. This is our reaction workup is messy. Now we will discuss dihydroxylation reactions. In late 1880s, Alexander Zevtsev and George Wagner, they empirically observation there, they when use that potassium permanganate in alkene oxidation, then they use the little mild condition, they change the temperature to cold from hot, and this alkaline condition is dilute. Also this potassium permanganate concentration is low, and they could find that syn dihydroxylation product are observed as the major product. Now how this happen? So this is the mechanism. We could see that initially we have find that alkene undergo addition to the permanent gives the cyclic manganate ester. Earlier we have find. Now from here the mechanism gets changed, that alkaline instead of breaking up this bond, carbon-carbon bond, the hydroxide undergo addition to the manganese center, and further the oxygen manganese bond cleavage happen and gives this alkoxide anion, and another then protonation happen. This is the alcohol, and at the same time again when this hydroxide undergo addition to the manganese, the similar way this manganese oxygen cleavage happen gives the anion, and protonation gives the alcohol. So this dihydroxylation happen, and this is as this manganese ester in the syn, so this cleavage also gives the syn dihydroxylation. So limitation of this reaction is that KMnO4 is the strong oxidant, so that cases we need to strict to control the reaction, low temperature need to control, and this is also the basicity also need to the dilute solution. These cases also we could find the low yield of this dihydroxylated product. As dihydroxylated product with KMnO4 given the low yield, so these dihydroxylations can happen with the another reagent with osmium tetroxide. In 90s to 1930s, scientists Makua, Hoffman and the Kriege, they designed and planned the alkene hydroxylation with osmium tetroxide. They could find the seen hydroxylation product. The mechanism of these reactions as well, osmium tetroxide reacts with this alkene double bond, generate the cyclic osmium ester, and further hydroxylation of this osmium gives this the osmium oxygen cleavage happen, gives this alcohol, and another center, another reacting site also gives the same way this alcohol. So dihydroxylation product form. And how this development happened? Initially, Makua in 1908 used the stoichiometric osmium tetroxide. Further development in 1912, Hoffman used the less amount of osmium tetroxide with the co-oxidant to get the better yield. And the Rudolf Kriege also 1936 increase the rate of the reaction by using tertiary amine and usually using the pyridine. Later, there are many development on this hydroxylations happen, gives the good yield of product, and also like Miller's hydroxylations, Abjon hydroxylations only use 1% on osmium tetroxide. These are the reaction conditions they have used. Limitation of these reactions is as osmium is highly toxic, osmium tetroxide highly toxic reagent, and this is expensive. Sometimes bulky substituent gives the poor reactivity, and so that's what. Now we'll discuss another interesting oxidation reactions of alkene is the ozonolysis. In 1903, the Carl Dietrich Harris he planned the ozonolysis reactions with different unsaturated hydrocarbon to analyze the structure, and he could find that if treated with alkene with ozone in solvent, it gives the two different types of carbonyl. And how this mechanism happen, we could find here alkenes reacts with ozone. This is found initially gives the monoozonide, and further rearrangement fragmentation happen, gives this way, gives this ion deuterionic compound and this carbonyl, and recombination gives the little stable ozonide compound. This is the ozonide compound, and further work of this ozonide with the different types of reagent. One either it is called the reducing agent, reductive workup, another is oxidation. If this type of means dimethyl sulfide or PPH3 zinc water are used for the workup, then ozonide decompose like this way, that dimethyl sulfide are attacked here of this peroxide bond here, and cleavage of the bond happen, and rearrangement gives this here. This part gives the ketone and this part gives the aldehyde as one hydrogen present, and further as a side product dimethyl sulfoxide form. So if this oxidative workup done by using the aqueous H2O2, then this way the reaction, this cleavage can happen, that peroxide cleavage happen, gives the ketone and aldehyde. Further, as it is oxidizing agent H2O2, it oxidizes the aldehyde, gives the acid. So the after ozonolysis, if you use the dimethyl sulfide, then aldehyde it remains as aldehyde and ketone. If you use the H2O2, the aldehyde converted to the acid. So different outcome will be there. Limitation of these reactions: ozone is a powerful toxic oxidant, and this ozonide is formed. This is explosive in nature, so require the cryogenic condition also for this reaction setting. And in this cases, as ozone is the high powerful oxygen, so there is no selectivity if there is many double bonds are there in the reaction, so all gives the cleavage of this double bond gives the carbonyl compound, so no selectivity is there. Now we'll discuss another oxidation reaction is the epoxidation, when alkenes treated with peroxy acid in different solvent, then epoxide is formed. This is three-member oxygen containing cycle called Oxyren and also known as epoxide. Now this is the concerted pathway. This mechanism happen when this alkene react with this end of this peroxy oxygen, and this happen through concerted way gives this epoxide and acid as the side product. This happen through the butterfly transition state, although this is mechanism initially not understand. Only discovery the Nikolai Philip have a 99 discovered, and the Paul Bartlett in 1950s given the mechanism of this epoxidation. The limitation of this reactions is if this alkene attached with the electron withdrawing group, that means this alkene is electron deficient alkene, so that cases reaction is not smooth or very slow or even not good yield give. And these reactions in non-polar substrate, if the reaction alkene is non-polar, that cases substrate is non-polar, solubility is issue, or so reactivity also not happen properly. As in these cases the reaction side product byproduct is the acid, so some if alkene attached with the substituent which is functional group which is acid sensitive, that cases is these reactions are little difficult to get the desired product. So why we should study the reactions of alkene? If we study the reactions of different reactions of alkene, we can find that it is essential to build complex molecule conversion of simple double bond to many different functional group. We expertise us on studying the reaction mechanism. We can understand which cases the Markovnikov product will follow, or which cases if it is Markovnikov product Markovnikov will follow, then outcome also we can understand. We can understand the stereochemistry of the product as well, if the reactions happen through the cyclic haloneum ion, then or anti-addition product form. Also different oxidations gives the same product. Application in industry, it creates different types of materials which is useful in our life, that it creates plastic, medicines and everyday consumer products, so only based on they are highly dependent on reactivity of alkene. Now we will move towards PYQ's discussions. First from JEE. Now first question, which compound would give 5-keto-2-methyl hexanyl upon ozonolysis? So first we have to draw 5-keto-2-methyl hexanyl, and then we have to just connect the double bond between two carbonyl carbon and remove the oxygen, then we can find the alkene. So here correct option will be this one. Now question number 2, the product of the following reactions given below. Here the reactions condition given NBS HNO. So allylic bromination happen. So there is two allylic position, which cases bromination will give the stable product, that way it will follow. Here in these cases, if radical formation happen, that cases this is stable compared to here because there is a strain if the brominations happen after radical formation. So that's why initially bromination happen once we part from this third butyl group and compared to 1 2, and then after formation of allylic bromination, that allylic substitution by hydroxyl group gives the product. So here correct option is the this one. Now 3-methyl 2-pentene on reactions with HBr in presence of peroxide given addition product, the number of possible stereoisomer of the product is, we have to find that, we have to draw first that, then that peroxide effect, hydrohalogenations we already know that, and this will gives the bromination and the less substituted position first, and then the radical addition of hydrogen gives this product. So correct option here, we could see these two chiral center here, possible stereoisomer 2 to the power n number of chiral centers. So here correct option is the 4. Question number 4, the major product of the following reactions is, here options, let's do that. First, bromination happen to this alkene and gives the cyclic bromonium ion. Further, the ethanol is the excess amount than this bromide, so ethanol attacks to this cyclobromonium ion. The reacting center among these two, this, because this side there is stability by the phenyl ring, so the product is this one. Now question number 5, identify the product A and B. Here dilute KMnO4 and 273 Kelvin means 0 degree Celsius, and then chromium trioxide oxidation. Let's do that. First, this one we know that dihydroxylations happen as cold dilute KMnO4, and then reactions follows this oxidation to this carbonyl center, this hydroxyl group via this way, and gives this ketone, and further this tertiary hydroxyl group give the that chromate ester which follow the elimination reactions gives this conjugated ketone. So correct option here this one. Now question number 6, what is the major product of formed by HI on reactions with this? This is the unsymmetrical alkene. Let's reactions happen like this way. First protonation, further this cases the secondary carbocation form initially, but the methyl group shift onto position, and then to the stable carbocation iodide undergo addition gives the major product. So here correct option is this one. Now question number 7, the product formed in the following reactions is, that is isoprene plus isobutane in presence of acidic condition. What are the product options given? Let's do that. That protonation happen to the olefin gives the stable carbocation, and then another unit of isoprene undergo addition to that. So this is the oligomerization reactions gives this carbocation. This double bond again move towards, and here positive charge form, and this is the isobutane reducing nature hydride shift to this carbocation and gives the product. So here correct option is the this one. Again from here this carbocation generated and undergo reactions. Now move to the question number 8. In the following given reactions, A is the major product, so we have to find the major product. Let's do that reactions. Here protonations happen from HBr, H plus come, and then gives the carbocation, then 1 to methylene shift because of steric strain, these expansions happen and gives the stable carbocation. Further towards more stable carbocation, methyl group shift 1 to position gives the 3 degree carbocation, and to that center the bromide attack gives the product. So here product is major product this one. Now question number 9, cyclohexene on ozonolysis further work up gives the compound Y, and Y further treatment with aqueous case yield the compound F. We have to find the product. Let's do that. First ozonolysis of cyclohexene via ozonide pathway gives this dialdehyde, this to center, and then that hydroxide undergo abstract the proton near the carbonyl group. It followed the aldol reaction, gives this compound, and further protonation gives this hydroxy, and finally dehydration gives the compound F. Here the correct option is this one. The compounds on hydrogenation produce optically inactive compounds. Means here options given among these following options, which are the alkenes gives the optically inactive compound. Let's do one by one. This one after hydrogenation gives this, here double bond comes as a single bond, but this center remains as a optically active center. Whereas this was optically active because this carbon contains 4 different groups, so it is chiral in nature. Now after hydrogenation, here this becomes the saturated part like this one, so that's why that chirality get diminished. These cases here hydrogenation gives this saturated single bond, whereas this center remains as like earlier, so chiral center remains as a previously not hampered chiral center, whereas this chiral center again get diminished by hydrogenation because one center contains two similar group. So here correct option is this one and this one. The two compounds becomes optically inactive. Now question number 11, in the following reactions the major product is, here this type of reactions we earlier have seen that protonations happen. One equivalent HBr gives the carbocation, and further this double bond shift gives the primary carbocation, and bromide adduct gives this product. This is the thermodynamically controlled product TCP. Correct option is this one. Thermodynamically product because it is giving the more substituted alkene. Now question number 12, the number of hydroxyl groups in Q. So you have to find. Let's do reaction. Protonations happen first. Here the protonation happen gives this hydronium ion, and then water removes gives the carbocation. Further 1,2-methyl shift here gives the stable carbocation 3 degree, and further the hydrogen from this center get eliminations gives this double bond. Now this two double bond undergo alkaline KMnO4 hydroxylation reactions at 0 degree Celsius mentioned. So this two double bond gives 4 hydroxyl group. So that's why number of hydroxyl group is 4. Now coming to the question number 13, in the following reactions the product S is ozonation first. Let's do that. Gives this two carbonyl means aldehyde, and then ammonia undergo addition to the more reactive aldehyde. This is more reactive aliphatic aldehyde, and like this way the mechanism happen. Further undergo ammonia addition gives the imine, and then its basic ammonia abstract proton and undergo reactions through enamine mechanism and gives this initial product, and further dehydration happen gives this isoguanolene product. So correct option here this one. Question number 14, the correct statements for the following reactions is or are. Here cis-butene and trans-butene undergo bromination reactions in presence of chloroform solvent. Here the different products given. Now this OP are identical molecules, and here M and O and P are the two pairs of diastereomer, whereas these are pair of enantiomer, or bromination process through trans-addition reactions. All the cases we can understand by doing that. Here cyclic bromonium ion form initially, and further rest bromide ion undergo addition to both the ion gives this mixture of product, whereas all products are the same. This is the meso product again, because this all bromo at the two center are the similar side, so each the center are this molecule has the internal mirror plane, so each optical activity are diminished by the other end optical activity, and so this is the identical molecule, these two. And whereas in case of cis butene, this cases cyclic bromonium ion happen, whereas these two isomers again gives the, we can see one is SS, one is RR, so racemic mixture form, two enantiomer form, and then these are two pairs of diastereomer, because this SS and SR are the diastereomer, and RR, RS are also diastereomers. Bromination process through trans-addition in both the reaction we have seen, as it happens through the cyclobromonium ion intermediate. Now these two options are correct options, and these are MO and NP are two pair of enantiomer. That is not true. Now coming to the question number 15, the compounds P and R undergo ozonolysis give QS, and whose formula is like this: one undergo Cannizzaro but not haloform, whereas S undergo haloform, not Cannizzaro. Let's do that. So here alkene options given. If that undergo ozonolysis, each will give this Q and S product. So this is the benzaldehyde, this is also this acetophenone, both formula C8H8O. This having CH3 group, it undergo haloform reactions, CH3CO, and this undergo Cannizzaro reactions, that benzylic CHO. So we could see this option is the correct option both the cases, because this cases also gives ozonolysis benzaldehyde, and this cases this part gives the acetophenone, whereas this cases gives the benzaldehyde, but this cases gives the acetophenone having the substitution, so that formula does not match. And again this cases also gives acetophenone function, whereas this extra methyl group, so the formula does not maintain. Question number 16. In the reactions given below, the total number of atoms having sp2 hybridization in the major product P is. We have to first determine the product P first. Let's do that. Ozonolysis and workup gives this tetracarbonyl product. Further reactions with that hydroxylamine gives this product. So here the total number of atoms having sp2 hybridization, this the atom which is attached to the double bond, both are sp2, so 4 carbon atom are sp2, and nitrogen auto atom also sp2, so total 8. Now question number 17, the number of CH2 methylene group in the product from the following sequence of reactions is. Let's do that. First ozonolysis here gives this aldehyde, generates 2 equivalent of aldehyde, 2 moles of. Further the cheminophore oxidations give acid, and NaOH electrolysis, that is the Kolbe process, gives the radical. Here decarboxylations happen, gives the propyl radical. Further this propyl radical undergo this way, undergo combinations, gives the addition, gives the N-hexane as the product, and further oxidation, the Cr2O3 gives the benzene. Now question number 18, list 1 contains various reactions, sequence list 2 contains the possible product. So match list 1 with list 2. Here this first one, let's do that. This cyclohexane gives this dialdehyde. Further NOH aqueous heat gives the aldol reaction product, earlier we have seen,
and then this ethylene glycol PTSA gives this protection of this aldehyde group, and further this BH3 diborane addition or gives this double bond addition of the borane. The less inner side bromine will come and gives that part as a alcohol, and this H3 plus again deprotections of this aldehyde gives this aldehyde function, and NMH4 reductions again that gives the alcohol. So final product for this will be this. For the second, we can see here again double bond cleavage by ozonolysis gives the one part here ketone, this side will give the aldehyde, and further aldol conditions reactions gives this product, and the same way protection and further this double bond hydroboration oxidations gives us alcohol this center, this protection and this side and reductions gives this secondary alcohol. So this is the final product. Again to this third one, this protection happen fast, then this oxymercuration reaction to the center gives this Markovnikov alcohol, the tertiary alcohol, this center, further deprotection of this gives this ketone, and then deprotection by dilute acid ester plus, and further this sodium borohydride reductions gives this tertiary alcohol to this center. And the last one, the same way, this protection, and then here this cases Hydroboration-Oxidation gives this alcohol in the less inner side, and further the reductions of this protection, deprotection gives this ketone, and reduction gives this tertiary dialcohol. So if we correlate, we can find this is the correct option. Now move to NEET.
Question number 19. Which of the following compounds with molecular formula C5H10 yields acetone on ozonolysis? So we have to draw its compounds. First one, we could see this could not form acetone. The second one, then 2-methyl 2-butene. If we ozonolysis, it can form the acetone. 3-methyl 1-butene. After ozonolysis, it can form acetone, and also cyclopentene can give the acetone after breaking of this double bond. So correct answer is this one. Question number 20. A predominantly formed in these reactions. Here the options we have to find. This is unsymmetrical alkene, H-bar addition, Markovnikov products generally formed. This side the stable carbocation formed, but here the hydride shift happen, so this carbon becomes the most stable carbocation 3 degree. That's why here bromide add happen, and product is the this one. Now question number 21. Identify Z in the sequence of reactions. So this is the in presence of peroxide, the hydrobromic acid addition, that cases the primary bromide will form initially. This cases further the sodium ethoxide undergo SN2 reaction gives this ether Z. Here correct option this one. Now question number 22. The reactions of this alkene with HBr produce which compound? Here we could see this first protonation give the stable carbocation this side, and then further bromide undergo addition to this carbon gives this product. Now question number 23. A single compound of the structure this obtained from the ozonolysis from which alkene? Options given here. Now if we join these two carbon and eliminate this oxygen, and we can find the alkene. So this is the correct answer. Now question number 24. A alkene A on reactions with ozone and followed by workup with zinc water gives the propanol and ethanol equimolar ratio. Then addition to HCl gives A and B. The major product we have to find. The structure of B is, so we have ethanol, propanol. If we combine, we get alkene, this one, and then the HCl addition happens like this way. Protonation gives the most stable carbocation, and then this is the product. So correct option this one. Now question number 25, alkene on ozonolysis gives the methanol as one of the products. So we have to determine the structure. Options given. So methanol means this structure. So if we could find that only this compound have this terminal double bond, that can gives the methanol after ozonolysis. So correct option is this one. Now question number 26, the major product of the following chemical reactions is here in presence of peroxide HBr addition. So that's why the terminal unsymmetrical alkene gives the terminal bromide, alkane bromide. So here correct option this one. Now question number 27, compound X on reactions with ozone followed by again zinc water treatment gives the formaldehyde and 2-methyl propanol. So we have to find out the alkene X. So that methanol means this is formaldehyde plus this 2-methyl propanol. So 1 2 3 2-methyl, and after combination we can find this alkene X. So this one 3-methyl 1-butene. And now question number 28, for this reactions we have to find the major product. Here options given. So we could find that oxidative cleavage happen here, gives this aldehyde, and further aldehyde undergo treated with acidic KMnO4. This way reactions happen and gives this acid. So here correct option is the acid. Now question number 29, predict the major product P in the following sequence of reactions. HBr benzoyl peroxide. So alkene HBr addition in presence of peroxide effect gives the less substituted bromide initially, and further reactions with CN cyanide as a nucleophile gives this one product by substitution reactions, and further reaction with sodium amalgam ethanol, the reductions of cyanide happen gives this H2NH2. Here correct option is this one. Now question number 30, given below as two statements. Statement 1, trans 2 butene upon treatment with Br2 in CCl4 gives the following product, and statement 2, cis 2 butene upon treatment with alkaline KMnO4 gives the following product. Now we know that trans 2 butene undergo treatment with Br2 CCl4 gives the meso dibromide, but if this is convert to the Fischer projection, we could find that this not convert to this. This is not, this is the trans one. So this statement is not true, means this product not formed. And in case of this one, this is the cis product. So because the alkaline KMnO4 cis hydroxylation happen, so this is true. So in this case, option 1 is the correct option. Now question from NSEC. Question number 31, the correct name of the product obtained is. So let's do that. Cyclohexene bromination gives the cyclobromonium ion. Further addition of bromide gives the product. So that is 1 2. This is the trans 1 2 dibromo cyclohexane. Now question number 32, which of the following statement is true for the reactions given below? Here cis butene undergo alkaline KMnO4 addition. So we have find that the meso product is formed, already discussed. So now question number 33, the main product is formed in the following reactions. This one, here the options given, we have to choose the product. Let's do that reactions. This NaOCl here, it acts as a base initially. So this abstract the proton gives the carbon ion, which is stabilized, and then it undergo nucleophilic addition to this chloronium of this NaOCl, and this COCCl3, and further hydroxide attacks here gives this acid. So right product is this one. Now question number 34, 1,3-pentadiene and 1,4-pentadiene are compared with respect to their intrinsic stability and reactions with HI. The correct statement is, we could find that this is 1,3-pentadiene, this is 1,4-pentadiene, this is conjugated one, so it can stabilize through resonance. That's why it is more stable than 1,4. There is no conjugation. And towards the reactions with HI, when initially protonation happen, it gives the more stable carbocation, whereas this cases also giving the stable secondary carbocation. There is no option for more stabilization through conjugation, but this case is stabilization through nearby double bond. So both the cases 1,3 pentadiene is more stable. Now question number 35, compound X reacts with diboron followed by alkaline hydrogen peroxide gives Y. So that means an alkene reacts with diboron gives the Y. Y should be alcohol, and Y reacts with sodium bromide in sulfuric acid followed by bromobenzene and sodium in ether gives the N-pentyl bromide. So now start with N-pentyl bromide. This is N-pentyl bromide. So sodium ether it formed during sodium ether reaction when bromobenzene treated with any this pentyl halide, as it is derived from treatment with sulfuric acid sodium bromide from alcohol, so it is N-pentyl bromide. That's why it is formed by Wurtz reaction. Now this alcohol is again N-pentanol, and it is produced from reactions with alkene when reactions with boron, diboron and alkaline hydrogen peroxide. That means this the less in the alcohol formed when it is from less substituted alkene. So here correct option is the this one. Now question number 36, the product X of the following sequence of reactions, we have to find the product. Let's do that reactions. Here ozonation gives this diketone, further reactions with sodium hydroxide, aldol reactions form, and then dehydrations, then protonation and further dehydration gives this product X. So this is the correct answer. Now question number 37, alkyl halide on reactions with ethanolic sodium hydroxide from alkene and further reactions with HBr gives alkyl halide. The alkene reactions with HBr peroxide with followed by magnesium metal followed by SN produces aldehyde Z. So we have to find what is Z. Now we could see that it is saying that alkyl halide reacts with ethanolic NOH gives the alkene. Again alkene reacts with HBr gives the same product. That means this is the possibility of alkene where we can find the same alkyl halide. It's undergo ethanolic elimination reactions give the alkene again. When treated with HBr peroxide, then terminal position bromination happen. So this is the bromide. And treated with magnesium, it gives the Grignard reagent alkyl magnesium bromide, and this acts as a this center acts as a nucleophile. When reacts with HCN, it attacks to the cyanide carbon and gives this imine magnesium bromide, and followed by hydrolysis acidic condition gives this aldehyde. Now we could see that if this R and R dash are H both, then this is the 1, 2, 3 propyl aldehyde only. There is no options for propyl aldehyde. When R or any R dash is methyl, then we could find, and any other is H, then we could find this N-butyl aldehyde. So that means 1, 2, 3, 4. That means this is the option 2. Now if both R and R dash are methyl, then we could find this product, this aldehyde. So this is the option C. So both the options are correct. Now question number 38, compound X in the following reactions is this ozonolysis further aqueous case means aldol kind of reaction setting. So let's this is formed again. So we have to find initial alkene. Let's do that. This is formed by aldol reaction. So if we aldol condensation reactions here, double bond form, we reverse gives the hydration product, and further retro aldol reaction gives this product. Now this again this center, if protonation happen, then it's become like this diketone, and again this if diketone we can eliminate the oxygen and connect with a double bond, we find the right initial alkene. So here correct option is this one. Now question number 39, which of the following on treatment with hot concentrated acidified KMnO4 will give 2-methyl cyclohexane 1,6 diacid as only the organic product? So we have to find which cases. Then let's react with this alkene with KMnO4. This first one, If treated with KMnO4, here oxidative cleavage happen, gives this acid, both the cases, and we name that 1, 2, 3. This is 3-methyl, not 2-methyl. This is dioic acid as well. If second one, here oxidative cleavage happen, gives the cyclohexanone plus formic acid, this part. And this one, alkene, if undergo reactions with hot KMnO4, this cleavage, oxidative cleavage gives happen also dioic acid, both the cases, and we could find that this is 1, 2, so 2-methyl. This is the correct option. This alkene the correct, again the option for this cases cleavage happen. This side gives the ketone and another side gives the acid. So 1, 2, 3, 4, 5, 6. This is not the dioic acid. So here only correct option this one. Now question number 40, that terpene N4 oil is an active ingredient in tea tree oil, has the following structure, this one, and the correct observations are. So first one is rotates polarized right. Yes, it has one chiral center, so it is optically active. It reacts with Bayer's reagent to form triol. Yes, it has a double bond. So Bayer's reagent are coal, alkaline, KMnO4. So it undergo hydroxylation reactions, gives the triol. Overall 3 hydroxy counts. The third one, on reactions with NaBr H2SO4, it gives dibromo compound. Yes, it's happened. Sodium bromide H2SO4 gives the HBr. So it's initially gives the here first the dihydroxylations happen, gives the carbocation, and then bromination happen. Further the HBr addition to this double bond means hydrobominations happen to the center, gives this product. And on ozonolysis it gives the compound with molecular formula this one. So ozonolysis happen to this double bond keto acid form. So that means 3 oxygen, so 4 oxygen atom come from acid part, here 2 ketone part 1, this one, and gives this formula. So this is also correct. Here 1, 2, 3, 4, all options are correct option. Now question number 41, addition of bromine to cis-3-hexene. Here the options we have to choose. This is the hexene, cis-3-hexene. So bromine addition gives the anti-addition product. We could find that here 2 enantiomer are formed. So racemic dibromide is the option. Question number 42, malic acid is a dicarboxylic acid present in apples and it has the following structure. Which of the synthetic routes will give the plus minus malic acid? Option 1, 2, 3, 4 given. We have to choose the right one. Let's do is synthetic pathway. The first one, HBr addition happen to this double bond, gives this bromide. Further aqueous cleavage gives alcohol, and these cases the HCN and H3 plus further does not undergo reactions for this. The synthetic path 2, here substitution of bromide by OH happen, gives the alcohol, and PCC oxidation gives this aldehyde, and further to this aldehyde cyanide nucleophile attacks undergo, gives this hydroxy cyanohydrin. Here this CN again undergo acidification, means hydrolysis gives this acid. So that cases we could generate the malic acid from synthetic 2 pathway. Let's check the synthetic 3. This cases CH3 CH2 COOH. So red phosphorus iodine gives the alpha iodination. Here at CH3 here this cases further NaOH gives this substitution of iodide to OH, but as CH3 present but there is no CH3 in the product, so this is not the right synthetic path. Let's check this one. Fourth one, here this acrylic acid undergo B2H6 addition oxidation, further gives this alcohol. So as this alcohol form, again oxidation is there, so this again path follow, and HCN addition gives this product. So that means this 2 and 4 are the right pathway. Now question number 43, an organic compound P with molecular formula C9H8O2 and on oxidation gives the benzoic acid. as one of the products. So possible structure of P is or are means we have to find the which one. Now let's do with this alkene. If oxidation of this gives this keto acid, further treatment with hydroxide gives this elimination of CO2 gives this hydrin, and KMNO4 oxidation gives this benzoic acid. So from this we can find benzoic acid, and this cinnamic acid undergo oxidation gives this benzaldehyde, this double bond, so this double bond, and benzaldehyde converted to benzoic acid again. Now this alkene 3 undergo oxidation through this double bond can give this phthalic acid, whereas this cases there is no double bond, it undergo not cleavage or oxidative cleavage. So only here two options are correct, 1 and 2. Now question number 44, the sequence of reagent required for the following conversion is, this is the conversion, choose, we have to choose the right set of reagent. Let's do one by one. This one is the substrate, reactions with this B2H6 H2O2OH minus gives this terminal alcohol, further reactions with sodium and ethyl chloride gives this ether product, but this is not matched. Now this one, reactions with HCl and sodium ethoxide, HCl addition gives this product, and further this substitution reactions happen, gives the initially the S1 pathway gives the carbocation stable, further addition of nucleophile gives this product. So this is the correct set of reagent. Now option 3, initially hydration gives this tertiary alcohol, reactions with sodium, this is the this alkoxide, this is the base, not nucleophile. So in this condition it does not undergo addition as well, and it even does not undergo coupling reactions with alcohol. So here only correct option, the option B. Now question number 45, the compound X in the following reactions is, so ozonolysis happen, that means this is alkene, we have to find the right alkene. This is not the alkene, so among these three we have to choose the product. Let's do that. This is the adipic acid, 2-carboxylic acid, that means it comes from this aldehyde function. So it's come from aldehyde function, means we need the 2-aldehyde. So let's first check this one. This ozonolysis gives this 2-aldehyde, that means this is not the this aldehyde, as substitution happened. This cases also we could see that this ketone is there, but here 2-carboxylic acid is there. So if this undergo haloform reactions, then it CCl3 form and undergo hydroxide attacks gives this acid. That means this is the right one, and let's check the other, as the 2 double bond is there, that means this cleavage of this 2 double bond gives this aldehyde acid, not this diacid, means adipic acid. So here correct option is only this one. Now question number 46, compound X in the following reactions is, here trans to cis alkene conversion or isomerization, we have to choose the right set of product. These cases brominations happen to the trans alkene, gives the dibromide product. Further with the strong base eliminations happen, gives this bromoalkene. Again another eliminations of HBr gives this alkyne. Then that hydrogenation to this alkyne, particular this palladium carbon and quinoline, this gives the cis product, so cis alkene. So here this right sequence is the 2 and then 1 then 3. Now question number 47, the reactions of 2,4-hexadiene with 1 equivalent bromine at 0 degrees Celsius gives the mixture of compounds X and Y. If X is 4,5-dibromohexene 2-hexene, then Y is, let's check this reaction. This is 2, 3, 4, 5, 6. So 2,4-hexadiene. Bromination gives the cyclic bromonium ion first, and then bromine undergo attack this side or from this side happen. At 0 degrees Celsius, the kinetically controlled product is the major product. So this addition happen gives the 4,5-dibromo-hex-2-ene here. And if thermodynamically reaction is get controlled, then this product will form. Means here bromine undergo addition and that double bond rearranges gives the product. So 2,5-dibromo-hex-3-ene product is formed as the another product. This is the major product at 0 degrees Celsius, and this is the minor product. So correct option is this one. Now question number 48. The two isomeric hydrocarbon X and Y give the same product on catalytic hydration with dilute acid. However, they form different product with same molecular formula when treated with excess bromine. We have to find XY. Let's choose this alkene. This one first. When they undergo hydration, they give the same product. How? This gives this carbocation, whereas this gives this carbocation initially, but this rearrangement happen gives both the same carbocation, and further water addition gives this alcohol. So same alcohol given both the product. Okay, but bromination, it gives the dibrominated product. Here this is anti, whereas this bromination gives this product. So that means the same molecular formula but different bromination product. So this is the right option, means match option. Let's choose the B. These cases we could find that during hydration, this carbocation from this alene type molecule, and these cases again hydration happen, this double bond this center, and or again this rearranges can give this alcohol. So that means, but these cases it forms this alcohol. So that cases this hydration does not give the same product. Option C, these cases we could find that hydration gives this enol for any of this end water added, and from these cases this side this enol formations happen, both gives the same ketone compound. So hydration of this option C, this alkyne, gives the same product, whereas bromination gives, we could find that brominations happen tetrabromo compound form in this cases symmetrical, whereas this cases at the 1-2 position that dibromide happen. These are not the same product. And option 4, if we see that this gives this hydrated product, means hydration product, this ketone, and this gives this alcohol, earlier we have seen. So these are not the same hydration product. So only option A and option C gives the same hydration product, this one and this one, and different brominated product. So here correct option this one and this one. Now question number 49. The alkene Y on the following reactions gives this product. We have to find out the alkene. Now let's see, these are the product form. We do that ozonolysis of each compound and we able to find out this product. From this option A, if we do this ozonolysis through double bond, we could find that this glyoxal one product, another is this formaldehyde product, another is the this keto, and this triketo. This is not the correct one. This compound B, if we do this ozonolysis, then this formaldehyde, this is one, another aldehyde keto CH2 aldehyde. So we don't have, this is also aldehyde keto, this we don't have this. Now if we do this ozonolysis of C, here we could find that this formaldehyde from this part, and another this breaking of this bond gives the methyl keto CH2 aldehyde. So methyl keto CH2 aldehyde, this part is there, this is there formaldehyde, and another part is this methyl keto CH2 CHO. So methyl keto CH2 CHO. So this is the right option we could find And this one, let's do D. This cases with formaldehyde okay, then methyl CO, again CO, CHO, methyl CO and no CO, CHO. So that means this is not the option here. Correct option only option C. Now question number 50. In a pair of isomers of molecular formula C5H, both the compounds undergo catalytic hydrogenation to form the compounds of molecular formula C5H10. On ozonolysis followed by oxidative workup, one of the compound gives diacid, another gives the ketoacid. So we have to find the pairs of isomer. Here the options given. Let's choose one option. Option A, 3-ethyl cyclopropene and 1 pentane. Here it is. So this gives the diacid, whereas this gives ozonolysis, gives the keto, this aldehyde to acid further. Here dialdehyde to diacid. Option B, this cases initially dialdehyde form and oxidative workup gives the diacid, and this cases this side gives keto and this terminal side gives the acid. Option C, this cases also we could find the this dialdehyde again gives the diacid, and here this gives the keto acid. And this option 4, here this end oxidative addition or ozonolysis, anyway it gives the diketone, not any keto acid, only this gives the diacid. So this option D does not gives the one keto acid or diacid. So correct option here 3 option 1 to 3. Now question number 51. At 0 degree Celsius, one equivalent of bromine is added to the 2,4-hexadiene and produces 4,5-dibromo-2-hexene and its isomer X. So what is the X? Already we have discussed. This is a repeated question. Option is the 2,5-dibromo. Question number 52. Predict the major product in the following reactions. This alkene undergo condensation. We have to find the proper product. Let's see the mechanism. Symmetrical alkene. Hydroboration followed by oxidation gives this alcohol, and further PCC oxidation at 0 degree Celsius gives this ketone. Here right product is this one. Now question number 53. The correct statement for 1,3-butadiene from the following are: these are the molar addition of Br2 only yields the 1,4-dibromo 2-butene as the major product when reactions is performed for a longer time period. Option B, molar addition of Br2 only yields 1,2-dibromo 2-butene for a longer time period. C1 C2 and C2 C4 bonds are slightly longer than CC double bond. C2 C3 bond are slightly shorter than the CC bond. This is a similar type of question because this the brominations happen give the KCP TCP product, this 1,2 addition and 1,4 addition. So that means this longer time gives the 1,4 addition product is the major product. And also this C2 C3 bond are slightly shorter than the single CC bond. So this is as double bond formation happen. So that's why the this C2 C3 bond are slightly shorter than single CC bond. Now question number 54. Consider the set of reactions. This one we have to find the product Q. This one hydroborations happen, further oxidations gives this alcohol, and further oxidation gives this ketone. So here correct option is the this one. Now question number 55. An unsaturated hydrocarbon oxidation oxidative ozonolysis gives the mixture of butane dioic acid and oxalic acid. The correct structure of hydrocarbon is, let's do that. So this butane dioic acid and oxalic acid are derived from this glyoxal and also this butane dialdehyde. Now let's do ozonolysis each of the compound. We could find that ozonolysis gives here this butane dialdehyde both the ends and also this glyoxal. So that means option A is the right option. Let's do option B, as triple bond is here, not double bond. So different product is there, not aldehyde. So different ketone type of product is formed. Option C, this cases we find glyoxal possibility is there, but there is the propane dialdehyde formation, not that butane. So these cases also you can find propane dialdehyde can form after cleavage, and another this keto aldehyde is formation possible. So here only correct option this one. Now question number 56, alkene can be converted to cis diols using osmium tetroxide, sodium bicarbonate, and trans diol via epoxide followed by acid hydrolysis. Compound C is given below, formed from which conditions we have to choose, means which alkene or which condition that is formed. Let's do one by one. This first option we could see that if alkene is cis or trans. Let's do that. This is cis alkene. When it is treated with peroxy acid, epoxide form, then hydrolysis gives the anti-addition product, so trans diol. But option C, it is cis diol in the product. So that means this alkene is not the alkene B, because if it is alkene B, then it is gives this product C, and not given the C, it is different product. So that means this cis alkene, not the alkene B. Now let's do trans alkene. Peroxy acid addition gives the epoxide. Further hydroxylation is given that this diol, this is actually have the mesodiol. If we rotate this bond, we could find this C actually this is formed. So that means this trans alkene gives the epoxide, means alkene B is the trans alkene, which after epoxidation gives the product C. So trans is the B. Now then if this cis alkene undergo osmium tetroxide oxidation gives the osmate, further hydroxylation gives the cis alcohol, so that is have the meso and mirror that matches with the C. That means this cis alkene is the alkene A, which undergo reactions with osmium tetroxide gives the product C. And if the trans alkene again treated with the osmium tetroxide, it gives the this trans diol, not the C. So that verification which gives that alkene A is the cis alkene which undergo reaction with this condition gives C, and alkene B are the trans alkene, this one which undergo reactions with the peroxy acid and followed by hydrolysis gives the C. So here correct option is the this one. Now question number 57, which of the following molecules react with ozone and hydrogen peroxide to form 1,4-benzene dicarboxylic acid, formic acid, oxalic acid, and acetone? So here the product given. Let's do ozonolysis and cleavage of carbon-carbon double bond. The first one, if we do cleavage, we could find that this part gives formic acid, this part is gives benzene dicarboxylic acid, this part gives acetone, and this part gives 1, 2, 3 propane dialdehyde. So we don't have propane dialdehyde, we have 1,4-benzene dicarboxylic acid, formic acid, oxalic acid, and acetone. So that means from there we could not find all the fragment. The second option, we could find here acetaldehyde, benzene dicarboxylic acid, oxalic acid, acetone. So formic acid is missing. That means this is not the correct one. So from this acetaldehyde we can find the acetic acid but not formic acid. Now this option 3, here cleavage gives the acetone, this both the end dialdehyde gives the dicarboxylic acid, again this dialdehyde 1, 2 gives the means glyoxal gives the oxalic acid, and this part gives the acetone. So that means this is the acetone, oxalic acid, 1,4-benzene dicarboxylic acid, oxalic acid, again acetone. So again formic acid missing from option C as well. Let's do this part. Get the formic acid from formaldehyde. This is 1,4-benzene dicarboxylic acid. This is gives the oxalic acid. This part gives the acetone. So this is the option D is the correct option. Now we will do next PYQs. Question number 58. The compound X undergo ozonolysis to yield 5-oxo-2-methyl-hexanal. The structure of X is, already we have discussed this earlier in the question 1 in JEE. So we could find that here this is the correct option. If we just connect this, we could find that. Now question number 59. The product obtained when the compound X is treated with NaOCl. This is the X compound. We have to choose the correct one. This is the repeated question as well. We have earlier seen. Here we could find that like this way the reactions happen and gives this product, the sodium carboxylate, as the major product. This is also repeated question. Now question number 60. At 0 degrees Celsius, one equivalent of bromine is added to 2,4-hexadiene produces 4,5-dibromo-2-hexene and its isomer X. X is also, this is discussed earlier, repeated question. Here answer is this one. Now question number 61. The main product of the following reactions is, here bromine water addition, initially cyclobromonium and intermediate form, further water is the excess in the reaction, acts as a nucleophile and it adds to that center where the stability of the carbocation is more. So here correct option is this one. Now question number 62. The number of optically active compounds obtained upon complete ozonolysis of the following compound. Let's do ozonolysis of this compound. Carbon-carbon double bond cleavage happen and gives this aldehyde product. 4 possible product formations happen as 4 cleavages there. So this one, this one and this one, this one. So now we could find that this compound are the same compound, because if we rotate this 180 degree, it gives the same compound through this axis. And whereas these two compounds are having the mirror image relation of each other, that means these are the enantiomers of the same compound. So their optical activity diminished one another. So that's why only optical active compounds are the one. So here correct option this one. Question number 63. In the addition of propane with bromine water, propane first reacts with bromine to form the bromonium ion intermediate, and bromide ion, the intermediate, reacts with bromine water to form the product as follows. The intermediate formed by the conversions of this 1 pi bond to 2 sigma bonds attached with the bromine plus, and the factors governing the yield of the reaction that depends on the concentration of the nucleophile. The correct statement is R. So nucleophile here is the water, it is present as a solvent, so major amount. So it is given 1,2-dibromo-propane is the major product. No, this is the side product, because this is water is the acts here. This most stable, most substituted carbon gives the major product, that is 2-propanol, 1-bromo, 2-propanol. And the hybridization of bromine in the intermediate sp3, because bromine is attached with all single bond, so sp3. And total number of optical isomer in this product mixture is 6, because we could find that these 3 products, these 2 are minor, this is major, so each having the chiral center. So for each chiral center there is another enantiomer, that means total 3 gives the another 3 enantiomer, so total mixture of isomer is 6. So these 3 options are the correct option. Now question number 64. The product of the reaction of styrene with diborane followed by alkaline hydrogen peroxide gives. So this is the styrene, that hydroboration gives this intermediate, further oxidation gives this alcohol. Here correct option is this one. Now question number 65. The ozonolysis of compound X shown below gives the P and formaldehyde. P is equilibrium with Q, and in Q all carbon-carbon bonds are equal. So the correct statement we have to find. Let's do that. This is X. After ozonolysis gives this fragmentation of this double bond gives the ketone, and this part gives the formaldehyde. So this is the P, and tautomization gives this Q. So this is paraglycinol, this is aromatic, and as this phenolic hydrogen is acidic nature, so Q trans blue litmus test. Okay. P forms a silver mirror with Tollens reagent. This is not true. This is ketone. Aldehyde gives this test. Q is aromatic. This is okay. And P reacts with hydrogen KOH gives this cyclohexane triol. No. This is Krishna's reagent. This ketone converted to methylene group CH2, not that alcohol. So only correct option this one and this one. Now question number 66. In electrophilic addition of olefins, the stability of carbocations plays a crucial role. Consider the compounds P and Q that undergo such reactions with different reagents. The first one, in the H-Bar addition, the rate of reaction faster for Q than P. So no, this is the methoxy group. If it forms the carbocation, it gets resonance stabilization than this one. So this is not the correct option. H-Bar addition to P gives the equal mixture of enantiomer as the major product. Yes, after this carbocation formation, the bromide undergo addition both the sides gives the mixture of enantiomer because it attaches with the 4 different groups, so chiral center. But this cases, the bromide addition gives the both the methyl are there, so no, this is achiral product. P reacts with diboron followed by H2 gives a racemic alcohol as the major product. No, this terminal double bond alcohol is formed, so this center is not the chiral center. That's why there is no question of racemic alcohol. Reactions of P with ozone followed by zinc water gives the methyl formate. Ozonolysis here gives the methyl formate. So this is also methyl formate and this part formaldehyde. So this is the correct. So both this option B and option D are the correct option. Now question number 67. Cyclohexene on reactions with one equivalent Cl2 in the presence of light gives P as the major product, which on reactions with one equivalent of NaI in dry acetone produces Q. The structure of Q is, let's do that here, that in presence of HNO, the chloride radical is formed that abstract the proton from this cyclohexene, the allylic position proton, and this is stable as stabilization through the double bond happen, conjugation, and then to that chlorination happen. This allylic chloride initially formed. When NaI react with this allylic chloride, then this way the reactions happen. Substitution, allylic substitution gives this iodo product. Here is the only product. Now question number 68. Cyclopentene is transformed into 1,2,3 tribromocyclopentane in 2 steps. The correct order of reagent required to carry out this transformation is, here the options given. Let's choose one by one. Step 1, Br2HNO and Br2CCl4. So Br2HNO, if step 1, then here this allylic dominations happen through radical formations, and initially this bromine adds to this position, then double bond undergo normal bromination in nonpolar solvent gives the dibromine. So total tribromine formation possible. But in the steps 2, if H-Bar addition happen, then to the double bond monobrominations happen. No allylic positions, allylic double bond available for brominations here. So this is not true. Again, so as initially that H-Bar addition happens, so this don't find the double bond to undergo addition. The C option, step 1, Br2CCl4, again if gets dibromination, then the third bromination not happen because not allylic double bond present. So this condition not sure. The option D, the one equivalent Br2HNO additions happen, monobrominations here, then HBr peroxide gives the again hydrobromination. So double bromination happen, not tribromination happen. So then only option 1 is the right option. Now we will discuss PIQs from CUET UG. The question number 69. In the following table, match the reactants given in the list 1 with the correct product in the list 2 as the product formed from the hydration reactions of alkene under acidic condition. So hydration of alkene under acidic condition, which substrate gives which product. Let's see that this gives this hydration product, Markovnikov product, all the cases. Here also Markovnikov product from this alcohol from this cases also this alcohol, and this cases gives this side the Markovnikov more substituted alcohol product. So to correlate, we can find that this is the right option. Now question number 70. The reagents used in the hydroboration oxidations of propene are, so hydroboration, this reagent first necessary, then this H2O2, and also aqueous sodium hydroxide is necessary. So then correct option is this one, you can find this. Now question number 71. Write the major product A in the following reaction. This cases in presence of peroxide, the terminal carbon gets the bromide. So here you could find that this one, right option this one. Now question number 72. What would be the major product when propene reacts with water in presence of acid catalyst? So we could see this reaction. This after protonation gives the most stable carbocation, secondary carbocation, then water adduct gives this propane 2-ol. Now we will move forward PIQs to IAT. Question number 73. These two different reactions, one hydrobromic acid addition normally in presence, another is in presence of peroxide. So we have to find that which intermediate, which cases are formed. Options given, we could see here, this is happens through carbocation intermediate and 2 degree, and this peroxide cases initially bromine addition happen that as a bromide radical, then it generates the 2 degree radical carbon radical. So here correct option is the 2 degree carbocation, 2 degree radical. Now question number 74. Major product P of the following reactions is, here unsymmetrical alkene. The reactions happen first protonation, further this side carbocation is more stable because of resonance. So again bromine attacks gives this product as the major product. Now question number 76. What are the major products formed in the following reaction sequence? These are the reaction sequence: ozonation, then reactions with Grignard, and this acidification. So first ozonation gives this aldehyde, and from this part it gives ketone. Then the 2 equivalents of phenyl magnesium bromide, it acts as a nucleophile, attacks this carbonyl center, gives this here to this alcohol, and to this product also another alcohol. So correct option here this one. The compound 1 undergoes hydroboration-oxidation reactions by this reagent boron and H2O2 and gives the another compound 2, which again undergo oxidation with chromium trioxide, gives this 2,3-dimethyl cyclohexanone as the product. So what is the structure of 1? Here the option given, we have to find it. Let's check the hydroboration oxidation is carbon, is this alkene. This hydroboration oxidation, here this cases alcohol will come the less inner side, and then oxidation gives this ketone. So we can find 1, 2, 3. So 2,3-dimethyl cyclohexanone is the product which is asked. So this is the correct option. Let's check the other alkene. These two, these cases, this here any one side of the alcohol come, so oxidation does not happen. This tertiary alcohol, these cases again here cleavage, here this any one side the alcohol come, this is the symmetrical side, so gives the alcohol, further oxidation gives the ketone, and we can find this 1, 2, 3, 4, 3, 4 dimethyl. This is not 2, 3 dimethyl, and these cases again here this side is the less inner side, alcohol will form here by hydroboration oxidation, and further oxidation it will give ketone, and we can find that this is 1, 2, 3, 4, 5, 6, this way 1, 2, 3, 4, 5, 6. So 2,6-dimethyl cyclohexane there, so not 2, 6, not 2, 3. So only correct option is this one. Now we will move to the NCERT book question. So question number 78, write the IUPAC names of the product obtained by HBr addition reactions to the X1 in presence of peroxide or in the absence of peroxide and in presence of peroxide. We know that this X1 in presence of peroxide, it gives the terminal bromide. This is 1 bromohexane, and in presence of HBr only, no peroxide effect, then Markovnikov product 2 bromohexane is the product. Now we will look some question from NCERT exercise. Question number 79, write the IUPAC name of the product obtained by ozonolysis of the following compounds. Pent 2 in, this one we have to draw this, then cleavage of double bond gives the ethanol and propanol. This one, the 3,4 dimethyl hept 3 in gives 2 butanone and 2 pentanone. By cleavage of this we could find this 2 ethyl but 1 in, after cleavage gives this formaldehyde and IUPAC name is methanol, and this one 1 2 3 4 5 3 pentanone, and this compound 1 phenyl but 1 in, after cleavage gives this benzaldehyde, can be called phenyl methanol as well by IUPAC name also benzaldehyde, and another part is this 1 2 3 propanol. Now question number 80, an alkene A on ozonolysis gives the mixture of ethanol and pentane 3-1. Write the structure. So if we combine this two keto, remove oxygen, gives this alkene 1 2 3 4 5, the same, and so this means 3 ethyl pent 2 in. Question number 81, an alkene A contains 3 CC bond and 8 CH sigma bonds and 1 CC pi bonds. A on ozonolysis gives 2 molar of aldehyde with molar mass 44 U. Write the IUPAC name of A. So now we could find that this aldehyde, one aldehyde having molar mass oxygen 16 and 2 carbon 24 and also 4 hydrogen 4, means 44. That means acetaldehyde having mass 44. So if the 2 molar of aldehyde means 2 acetaldehyde are formed by the ozonolysis, then the combination gives this alkene, the parent alkene, that means butene, trans-butene or cis, any one. Now we could find that here 1 CC single bond, double bond is there, and single bond 1 2 3 single bond CC, and CH bonds are 3 3 6 and 8 CH bonds. So these are the alkene A but 2 in. Now question number 82, propanol and pentane 3-1 is the ozonolysis product of an alkene, and what is the structural formula of alkene, give the reactions mechanism. So if we combine these two products, then we can find this alkene. The mechanism of this ozonolysis we have already discussed. Now question number 83, write down the ozonolysis product of 1,2 dimethyl benzene, that is called orthoxylene. How does the result support calculus structure of benzene? Now if do the ozonolysis of orthoxylene, the 2 methyl are the ortho position, 1 2 position ozonolysis. If the double bond are in this orientations, then it gives this way one glyoxyl, this way another glyoxyl, and this way this dimethyl, this diketone. And if this double bond are this orientation through this CC bond and this way, then cleavage it gives this ketoaldehyde 2 moles and this glyoxyl 1 moles. If we designate that glyoxyl as a B and this ketoaldehyde A and this diketodimethyl is C, then generally it was observed that ratio of this was ABC 2:3:1. So that means it observation says that this ratio product is formed. That means when this xylene, in the xylene double bond are the resonance of this two hybrid form, means benzene are in the two different resonance, the alternative structure of double bond are present, so that supports the calculus structure. Now coming to the question number 84, write structure of all the alkenes which on hydrogenation gives the 2-methyl butane. So this is the 2-methyl butane structure. Now here if double bond can have present, this side also double bond can present, this side also double bond can present, and this side double bond present. So this side double bond and this side double bond are the same structure. That means this one hydrogenation gives this one. This is methyl, this is methyl. So this any double bond gives the one isomer. This one hydrogenation gives this. Here this internal double bond gives also this one. This alkene gives this, and this butene are this terminal side double bond also hydrogenation gives this one. So three possible alkene that gives the 2-methyl butane. Now, so hi guys, thanks for watching, and please subscribe if you want to get more such videos. Please comment if you have any doubts, and like, share to move forward. So thanks again.